I am Andrew Fraser, and I will be presenting my thesis on spatial error estimation for collocation solutions of differential equations. The first few topics which I will cover today are more general concepts, while the following topics will become more specific into the work done as part of my thesis. The first concept I'll introduce is mathematical modeling, which is the idea that mathematical equations can be used to model real-world phenomena. For example, here we see the velocity of an object accelerating at 2 meters per second squared. While this is a simple model, it is still a mathematical model. We can also model much more complex phenomena, such as the diffusion of heat or the spread of a brain tumor. Although most of these models do not have a closed-form solution, so we can instead compute numerical approximations to the solutions to these models. Although not all numerical approximations are the same. Here we see two different approximations for the solution of the same heat diffusion model. And note how much these two approximations differ. Which one is closer to the exact solution? So clearly one of them is better, and that gives rise to the question of how can we tell how good an approximation is? This leads us to error control. So since these are numerical approximations, there is error associated with them. And error estimation allows numerical software to return a solution approximation along with an estimate of the error. One step above that we have error control. And error control software allows the user to specify tolerance, which gives an upper bound on how large the estimated error of the computed solution is allowed to be. Software using error control will try to meet the specified tolerance while minimizing the amount of work required. Using error estimation, the software can detect if the tolerance is not being satisfied and adapt the computation to obtain a numerical solution whose estimated error does satisfy the tolerance. I will now begin to talk a bit more specifically about some of the work done within this thesis. So for this thesis, we considered various types of differential equations. These cases represent one-dimensional time-dependent and time-independent, and also two-dimensional time-dependent and time-independent problems. And all of the methods used within this thesis for calculating approximate solutions and error estimates are highly generalizable between these problem classes. Our first problem class is the boundary value ordinary differential equations. This is the one-dimensional time-independent problem class. The general form considered includes the following: the ODE, the spatial domain, as well as the boundary conditions. And below here we see one of the test problems used within this thesis. Here we can see the true solution to that test problem, and we can see that the solution is a function across one spatial domain. The next problem class we have are the parabolic partial differential equations. This is the one-dimensional time-dependent problem class. The general form for this includes the PDE, the spatial domain, a known initial condition, and once again boundary conditions. At the bottom here we have one of the test problems used within this thesis, and here we can see the true solution to that test problem. So now once again we can see we have a function plotted across one spatial domain, but we also see the temporal domain here where that function moves through time. Our third problem class are the elliptic partial differential equations. These are the two-dimensional time-independent problem class. The general form for these includes the PDE, the spatial domain, and in this case we have boundary conditions along all four boundaries of these spatial domains. At the bottom here we also see one of the test problems used. And here is the true solution to that test problem. And in this case we see we have that X and Y spatial domain here, and then that one output domain. Our final problem class are the two-dimensional parabolic partial differential equations, and these are the two-dimensional time-dependent problem class. The general form for these includes the PDE, the spatial domain, known initial conditions, and just like the elliptic case, we have the boundary conditions across all of the boundaries of the spatial domains. And then here we see one of our test problems used. And this is the true solution to that test problem there. And here we see as the EPDE case, we have that X and Y domain and that output domain, but also we have the temporal domain where that function changes as time progresses. Now that we have introduced our different problem classes, we can then ask, how can we calculate a numerical approximation to the solution of these differential equations? In the approach we consider in this thesis, we will represent the numerical solution approximation as a piecewise polynomial with unknown coefficients. In the one-dimensional case, the spatial domain is split into subintervals, with each subinterval having a polynomial defined over it. The two-dimensional cases are split into subrectangles. And these piecewise polynomials are determined through their unknown coefficients. For example, a piecewise quadratic would have the unknown coefficients a, b, and c as seen here. And here we have just a quick example of a piecewise polynomial. Although we use B-spline basis functions to define our piecewise polynomials, and to create a piecewise polynomial of degree p over n subintervals with C1 continuity, meaning that the solution value and the first derivative are continuous, requires a known amount of B-spline basis functions. And here in this picture we can see the B-spline basis functions that are required for defining a piecewise polynomial of degree 4 over 3 subintervals. On each subinterval, the piecewise polynomial is required to exactly satisfy the differential equation at certain points. These points are called collocation points. The resulting equations are called the collocation conditions. And even though the approximate solution satisfies the differential equation only at certain points in the domain, it can be shown that it gives a good approximation to the exact solution throughout the domain. The unknown B-spline basis coefficients are determined by solving the equations corresponding to the boundary and collocation conditions. These equations form a nonlinear algebraic or differential algebraic system which is solved using software with error control. After the system has been solved, we obtain B-spline basis coefficients, which means that we have our numerical approximation to the solution to the differential equation. As mentioned earlier, since it is a numerical approximation that we have computed, it has an error associated with it. So, how do we compute this error? In this thesis, we consider one class of error estimation algorithms based on interpolation. Ideally, we'd be able to look at the difference between the true solution and the approximate solution to figure out the exact error, although since we don't know the true solution, we can't just look at this difference. Instead, we can substitute for the true solution with an approximate solution that is more accurate than our original approximation, and look at the difference between those two to get an estimate of the error. So we're going to be looking at the difference between a better approximate solution and the original approximate solution to figure out our error estimate. Although computing a collocation solution is computationally expensive, and computing a better collocation solution would be even more computationally expensive. This would end up having us spend more time estimating the error than actually computing the approximation which we return. However though, it turns out that we can use an interpolant to our collocation solution to get a better approximate solution without much extra computational cost. How this happens is when the collocation points on each subinterval are chosen to be what are known as the Gauss points, it turns out that there are certain known points on the subinterval where the collocation solution is of higher accuracy than elsewhere. Here we see the true error of a collocation solution with one subinterval and degree 4 plotted here. We see those dips in the error at the ends of the interval, and then also we have these 3 dips within the subinterval that are of known points. And these points are also known for any degree of collocation solution. So, by choosing our interpolation points where the collocation solution has higher accuracy, we can create an interpolant whose accuracy across the domain is higher than that of the collocation solution. And this gives us the higher accuracy approximation that we can use within the expression for the error estimate. Here we see again that error plot of that collocation solution, but here we also have in the dashed blue line the error estimate provided from this method we just described. And so you can see that that error estimate is not exact, but it is still close enough to provide a reasonable error estimate. This is because most of the time just one digit of precision is sufficient for an error estimate. For example, we don't gain much by knowing if an error is 5.2 times 10 to the minus 3 instead of 5.4 times 10 to the minus 3. But knowing if an error is 5 times 10 to the minus 3 instead of 4 times 10 to the minus 2 can make a difference. So after the error estimate is calculated, as mentioned earlier, we can then talk about error control. So I'll quickly show one way this can look for collocation solutions. So here we have an approximate solution, the error of it plotted, and we see three subintervals having higher error. What we can do is, by subdividing these subintervals, we can reduce the error across this region. And so here we see this zoomed into those three difficult regions. Those solid lines are the subintervals we used for that green collocation solution, where we've also added in these dashed lines in between each of those that define the subintervals for that collocation solution, which is represented by that blue dashed line. And we can see the error in that region is much lower. I will now talk about some of the testing that has occurred as part of this thesis. One method of creating a more accurate interpolant is based on what is called a superconversion interpolant, or SCI. In my thesis, the SCI has been generalized from 1 to 2 spatial dimensions. Another approach for error estimation is to use an interpolant of one order accuracy below that of the collocation solution. This involves the use of what is called a lower order interpolant, or LOI. In my thesis, the LOI has been generalized from 1 to 2 spatial dimensions, and also in my thesis we introduce a new interpolant, the LOI2. The performance of these error estimation methods was tested for problems of the BVODE, PPDE, and EPDE problem classes. The collocation software developed for the 2D PPDE problem class does not perform as expected, and thus it cannot be used to test the error estimation methods. Also, a scaled version of the LOI and LOI2 were tested. These include a scaling that attempts to correct for overestimation of error due to the interpolant being an order lower than the order of the collocation solution. And what are we looking for from these error estimation methods? So it is desired that they're able to provide an error estimate of the correct order. To visualize this easier, we plot the log error ratio, where the plotted error is the base 10 logarithm of the estimated error divided by the actual error. And what this does is, when this value is 1, that corresponds to having an error estimate which is one order above the true error. Negative 1 means we're one order below, and 0 corresponds to the actual error. Here we can see the results from one test in the BVODE problem class for a collocation solution of degree 5 with 32 subintervals. On the left plot, we see the error estimates of each subinterval across the spatial domain for each of the interpolants. And on the right, the vertical axis also represents the log error ratio, but the horizontal axis tells us the occurrence of those estimates. In this problem class, the SCI performs very well, always providing an error log ratio close to 0. The LOI is almost as consistent as the SCI, but tends to overestimate slightly, although it does not approach an error log ratio of 1. The scaled version tends to produce an error log ratio of about 0.2 lower. The LOI2 performs very similar to the LOI, although produces an error log ratio of about 0.1 lower than the LOI. The scaled version tends to produce an error log ratio of about 0.2 lower, and within all of these methods there's a downwards tendency in the error log ratios as the degree of collocation solution increases. Here we see the same style of plot for the PPDE problem class with p equals 5 and n equals 32. In this problem class, the SCI becomes less consistent for degrees of collocation solution that are greater, although it still provides an error estimate of the correct order, providing an error log ratio between negative 0.7 and positive 0.1. The LOI provides error log ratios between negative 0.5 and positive 0.5, while its scaled version falls between negative 0.7 and positive 0.3. The LOI2 provides error log ratios between negative 0.5 and positive 0.3, while its scaled version falls between negative 0.8 and 0. Within all of these methods, there is again a downwards tendency in the error log ratios as the degree of collocation solution increases, although it is more pronounced in this problem class. Here in the EPDE problem class, our plots look a bit different. In the top left, we see the error estimates on each subrectangle across the spatial domains from the SCI. In the bottom left, we see that for the LOI and LOI2. The top right, the LOI and LOI2 scaled versions. And in the bottom right, we have once again that occurrence rate plot. In this problem class, both the SCI and LOI are not able to perform well. Both of these methods require collocation solution derivative values of sufficient accuracy, which is found not to occur in a collocation solution for this problem class. And this has motivated the creation of the LOI2, which does not rely on derivative values. Thus, in this case, the LOI2 performs well, providing an error log ratio between negative 0.5 and 0, while the scaled version is between 0 and positive 0.5. Now, concluding the results of this thesis, this included the development of collocation software in Scilab for the various problem classes, along with numerical convergence results which confirmed the expected convergence rates. The pre-existing SCI and LOI error estimation methods provided results showing they provide an error estimate of the correct order in the BVODE and PPDE problem classes, and the new LOI2 error estimation method was able to provide an error estimate of the correct order for the BVODE, PPDE, and EPDE problem classes. Some future works from this thesis. The first one is that Scilab is not a very efficient language, although good for prototyping, and the process of computing a collocation solutions in 2 spatial dimensions could be greatly sped up by implementing the algorithm in a compiled language such as Fortran, which is widely used in scientific computing. Another opportunity for future work is that high-quality error control software exists for PDEs with 1 spatial dimension, although error control software for time-dependent PDEs with 2 spatial dimensions has not yet been developed to our knowledge. Finally, the 2D PPDE collocation software, as mentioned, does not perform as expected, so a further investigation could resolve these issues and be followed by an evaluation of the error estimation methods in this problem class. And that concludes my presentation, so thank you for following along. If you have any questions, feel free to send them by email to me at this email here. And here are some of the references used within this presentation.